the different meta-heuristic techniques that has been applied in antenna engineering. Now, let us study how to effectively use this for antenna designing. Right. Before that, let us see what are the capabilities of these meta-heuristics, or let us see what kind of problems these meta-heuristics can solve. So techniques like ANN and fuzzy logic, they can solve these two type of problems. One is first one is suppose you have a bunch of data, and corresponding to each data you have a corresponding output, and you don't have the idea about the relationship between this input and output data set, then these ANN fuzzy logic techniques can be used to form a mapping between these two data sets. In mathematics, we are calling it as a function mapping type of problem. So function mapping type of problems can be solved with the help of these meta-heuristics. Another kind is suppose you have a bunch of data, but you don't have an idea what kind of data you are having. Then these meta-heuristics can be used to classify those data set. So if you use these techniques that can tell you that I have some data of this type, some other data of this type, so on and so forth. So in mathematics, we are calling it as classification type of problem. So function mapping type of problem and classification problems can be solved using these two meta-heuristics, ANN and fuzzy logic. All others like genetic algorithm, particle swarm optimization, bacteria foraging optimization, ant colony optimization, those techniques, as the name indicates, mostly these are optimizers. So optimization problems can be solved using these techniques. Here is an example, the same example that we have studied earlier. You have a function of two variables, and the range of the variables are given. Those are the restrictions, and within this range you need to find out the peak value of this function. So if you apply so any of these meta-heuristic techniques can be used to solve this kind of problems. So if you apply any technique, it will give you the result, location on the surface of the peak function or global maximum. So now broadly we have classified all the meta-heuristics into two categories. One category can be used for solving like function mapping type of problem and classification problems, and another set of meta-heuristics, those can be used, those techniques can be used for solving optimization problems. Those are basically optimizers, right? These are the actual snapshots of the initial random data that you are choosing while applying any of these optimizers, and you can mark with the number of iterations gradually both all these random possible random solutions are approaching towards the actual solution of that particular problem, that two-dimensional XY problem. Okay. And why to go for these meta-heuristic based optimizers? Because these optimizers are having their own problem. These problems are like classic optimizers are only time consuming. These techniques of optimization fail to deal with complex problems in multiple parameters. So with the increase in number of parameters, the complexity of the problems increases, and in those cases, it is very difficult to apply the classical optimization problems. These are local search methods and involve the derivative technique. If you apply the classical optimization technique, you need to find out derivatives. But there are situations where you can't find a derivative at a particular point. These techniques are computationally unstable or less efficient, right? Whereas if you go for these machine learning based optimizers, this can handle many variables simultaneously. In fact, ideally, this can handle any number of variables, whatever may be the number of variables that are available in that are required in solving a particular problem. It can they can handle any number of variables. Use of these global optimization methods can avoid the chances of trapping local minima if the problem in hand can be formulated as an optimization problem. Although whenever people are devising a particular machine learning based optimization technique, although they are claiming that this is a global optimization method, but rare situations are there where those techniques are also failing to give you the exact solution. But the important point in these meta heuristics is, or these optimizers, is that they provide low cost solutions. And as far as antenna engineering is concerned, this is important because almost all these microwave engineering problems are costly problems. Costly in the sense the simulators, not only in monetary wise, but also like time of computation, if you see, and complexity of the problem, if you see, those are all like costly problems. Okay. But these optimizers, they provide a low-cost solution, thereby reducing the dependency on costly electromagnetic simulators up to some extent. Furthermore, these methods are adaptive and scalable. Okay, that means you can increase the accuracy of these methods by applying them again and again, or by developing them again and again. Okay. Oh, I don't know why I'm getting this type of problem. Just a second. Uh, Okay. Now let us see a typical antenna design problem. So we're calling this as a conventional design approach. So any antenna problem is actually approached in this way. We start with an approximate model. Approximate model means depending on the closed form formula that are available with us, or using our own experience, we are choosing the different dimensions of the antenna or different parameters of the antenna. Then we are observing its performance, the antenna performance. So if the performance of that approximate model, if it is matching with our requirement, we are taking that as our final design. Or if it is not matching, then we are changing the parameters. And usually in antenna designing, a lot of parameters are involved. So we are changing those parameters. Again, we are observing the performance of that changed antenna. If it is matching our requirement, then we are taking that final design, or we are doing this iterative process of changing the design parameters. Okay. So if you observe this conventional design approach, at this particular point, we are using simulator. That means after developing the approximate model, or after designing the, after changing the approximate model a number of times, in order to observe its performance, we need a RF simulator, right? And if you see mathematically, each time we are changing these parameters. So mathematically, if you see, basically we are applying an optimization process at this point. So here we need the requirement of simulator is there. Here at this stage, requirement of an optimizer is there, right? Now these two things, these two, the roles of these two places can be replaced by suitable meta-heuristic technique. Okay. Now, because of now, why one should go for using meta-heuristics at these two places? Because the having a simulator is costly affair, and each simulator is having their own simulation time. And at this point, classical optimizers have their own demerits, so on and so forth. And because of which the antenna design process becomes a costly affair, right? So these two places can now be replaced by suitable meta-heuristic techniques, right? So this conventional design approach can now be replaced by this particular approach. Okay, what is that particular approach? The role of the simulator can be replaced by a suitably trained artificial neural network, and the role of this optimizer, where previously we are doing it by a trial error method, arbitrary trial error method, that can be replaced by any of these meta-heuristic based optimizers. Okay, here in this particular I have written PSO, particle swarm optimization, but any of these meta-heuristic based optimizers that we've studied can be used at that particular place. So what exactly you are gaining if the previous process is replaced by this particular process? The response time of this ANN is very fast, although it takes a huge amount of time for training and testing. But once trained properly, the response is almost instant. So in that way, you can avoid the requirement of a simulator. Not only that, you can avoid the simulation time. Okay, the simulation, each simulator is having their own simulation time, right? And furthermore, the previous method of changing these parameters was arbitrary in nature. But in place of that, if you are applying a meta-heuristic based optimizer, your changing of these parameters in each iteration or in each loop path becomes systematic. Okay, so in a systematic way, you are going to vary the parameters of the antenna, and because the response time of this, the computation of these time of these optimizers is also very less, and the response time of ANN is very fast, so you can have a very fast design approach for, you can develop a very fast design approach for antenna designing. Okay. Now here the ANN, as we have studied, ANN can solve two different types of problems, some function mapping type of problem and the classification type of problem. So here the ANN, the role of the ANN is to play that function mapper, or it is basically solving that function mapping type of problem. And here the optimization, meta-heuristic based optimization, PSO, is solving an optimization problem. So although you have different meta-heuristic techniques, depending on their capability or depending on the type of problem that they can solve, you use a combination of those meta-heuristics to solve your own antenna problem. Okay. So let us see an example of applying this technique. Although we have used this technique to find out different antenna solutions, let us say see this typical example. is designing a custom-made Koch monopole design, right? So on the right-hand side, you can find out the shape of a Koch monopole antenna. It's a planar antenna. It's basically a fractal antenna, and those who are engaged in antenna designing or antenna research, you must be knowing that fractal antennas are multiband antennas, right? And for any classical fractal antenna, you can have, depending on the number of iterations that you have applied to create that antenna, you can get that many number of frequencies out of that fractal antenna. But the demerit of those classical fractal antennas is that first of all, the frequencies that you are getting from a classical fractal antenna, all the frequencies are not user-defined frequencies, or all the frequencies are not the required frequencies. We can't use all the frequencies at the same time, right? See, so if, for example, if one frequency is coming at suppose 2 gigahertz, another frequency is coming at 4 gigahertz, third frequency is coming at 6 gigahertz, right? But we don't need those 4 gigahertz frequencies. Suppose I need that 4.8 gigahertz frequency. So I can't use that classical fractal antenna. Although I need one frequency at 2 gigahertz, the second frequency I need at not at 4. I need at 4.5 or 4.8, right? So you need to change the shape of those classical fractal structures. Okay, you change the parameters of that fractal structure so that the correspondingly it will change the resonant frequency of that fractal structure. As far as this Koch monopole antenna is there, the parameters are the total length of the antenna or monopole, the L, and in each iteration you are creating this structure, and each side is of same length with a certain angle theta. But you can play with this theta angle. First time you can make it theta, second time you can make it theta 1, and so on, so that you can shift those resonant frequencies of the antenna. So in this case, because all resonant frequencies of a classical antenna are not required frequencies, so we have used this angle as another parameter to shift those frequencies. Okay. Now the analysis problem is easy. That means you have a specific L, you have a specific theta, you have a specific theta 1. From that you can find out the resonant frequencies. But my problem is not that one. My problem is to design the antenna. That means I want the antenna to resonate at specific frequencies 1, specific frequency 2, specific frequency 3. For that, what should be my L, what should be my theta 1, and so on. That is the design problem is actually challenging, not the analysis problem. Okay, so we have used this particular method to implement our design process. So first step is to design the trained neural network model for different L, theta, theta 1. We calculated the resonant frequencies, we calculated the impedances and the bandwidths at those frequencies. Okay, and a trained neural network model was developed. Okay. These are the parameters of those training data or the neural network. This is the neural network for different L, theta, theta 1. We calculated these values. That is the first step of implementing that design process. Then in this particular case, we have used this particle swarm optimization, but you can use any of these meta-heuristic based optimizers. Each optimizer, to implement those optimizers, each one is having their own set rules. You follow those set rules and write your own code. But in each of these cases, you need to define the cost function, so that with iteration the cost function will gradually approach towards 0. So using this method, we have designed number of typical antennas working at different frequencies. These are few of the results, few dual band antennas that we designed out of this for this Koch monopole antenna. Okay. For example, the first one, antenna 1, it will work at 2.4 and 5.25 gigahertz. Okay. But in classical fractal structure, if first frequency is 2.4, mostly you are going to get the second frequency at 4.8, something like that. But I don't need that one. I need my second frequency as 5.25 gigahertz, right? So for different fractal structures, you have different parameters. By playing with those parameters, you can shift those resonant frequencies. Similarly for other antennas. Then we have developed our own PSO code, and that was in the PSO code. Within that PSO loop, the trained neural network was placed. So as I showed you in the previous slide, the job of that inserted neural network was to give the response parameters of the antenna, resonant frequency, bandwidth, and impedance for different dimensions of the antenna. Okay. So we have applied that one, and we have used this simple cost functions, because in first antenna designing problem, my requirement is these two resonant frequencies, 2.4 and 5.2 gigahertz. So I have used this simple fitness function, the 2.4 minus f1 square plus 5.25 minus f2 square. Okay. And in each iteration of that optimization loop, you are going to get one set of f1 and f2, right? And that particular value will be compared with your required or desired values of resonant frequency, right? And that particular error will be used for finding out the next set of solutions in that optimization loop. Okay. So standard algorithms are available in PSO. Here we is used PSO because it is simple and easy to apply. The coding is not that lengthy. Okay. And we got by using that particular process ANN inside a PSO loop, we got these results. Okay. For the first antenna, for getting these required resonant frequencies, I got this value of L, this value of theta, and this value of theta 1, right? So you take these values and fabricate your antenna. This is this monopole antenna in this particular case. Similarly, for the second case, third case, and fourth case, we got this value of L, theta, theta 1, and so on. But the most important thing to mark is the computation time. For these frequencies, to design a dual band antenna, to get the parameters, the design parameters or design dimensions of the antenna, you can mark from this last column. It just takes few seconds of time to get these results. That is the beauty of applying these meta-heuristic based techniques. Okay. So what exactly we did? We used two different types of meta-heuristics because their capability of solving problems is of different types. So we used those two particular things and we used a trained neural network inside the optimization loop of a PSO, and because of which we got this efficient method of antenna designing whose computation time is very less. Now suppose think of a situation. Suppose you have not used ANN in this example. So what is the other solution? You need to insert an RF optimizer inside an PSO or any other optimizer. So in each iteration, the optimizer will create a possible set solution. That means one set of L, theta, theta 1. By taking those L, theta, theta 1, with the help of the simulator, you need to draw that particular thing, that structure, and then you simulate that structure using the RF simulator. It will take some time, and the output of that means the resonant frequency, bandwidth at different frequencies, and impedance at different frequencies, you use that again as the output from that simulator. Use that inside the loop. Okay, and again that has to be inserted inside the neural network. So again the computation time will be very large in that particular case, because for each set of outputs that you are getting from the neural network, you need to feed that to the RF simulator, and again the RF simulator output, to find out the RF simulator output, it will take some time. Okay? So the computation time will become huge, and second thing is you need a RF simulator for that. Okay. So that will be the problem if you are not using a trained neural network and you are using only an optimizer. So by judiciously using different meta-heuristic based methods, it is possible to reduce the computation time of antenna designing process. Okay. So using that method, these are the four designed antennas, dual band antennas, although it will work at 3 frequencies, but we are not bothered about, we are not concerned about that third frequency. So the shape of the optimized Koch monopole antennas are these 4 figures, and all the shapes we calculated, we derived from by applying those ANN and PSO loop. Okay, so let me give you the concluding remarks of today's talk. What are the things we have discussed? We started with the meta-heuristic techniques, their capabilities, the type of problems that can be solved using the meta-heuristic techniques, and where to apply the meta-heuristics, where not to, that we have discussed. For example, if you have closed form formulas available, then don't go for these neural network techniques, right? If it is a complex problem and the relationship between the input and the response is highly nonlinear, highly complex, then only go for this neural network technique or fuzzy logic. Otherwise not. If you have closed form formula available, use that one and try to find out your answer. Similarly, if it is a simple optimization problem, better go for classical optimization technique. Don't go for this meta-heuristic based optimization technique, right? Simple like minimum number of variables and having minimum number of maxima minima, then you better go for classical optimization techniques. So that we have discussed. But most of these antenna problems are very much complex and very much highly nonlinear in nature. Then we have discussed this one, a fast, flexible approach for design of custom-made systems. Custom-made system is depending on the requirement, because nowadays you need mostly multi-band antennas. Most of these wireless communication systems, they need multi-band because number of tasks it has to perform. So you need multi-band antennas. So we discussed a method of designing multi-band antennas that should be fast and flexible with the help of different type of meta-heuristic techniques. We discussed what should be the approach, because we verified that one set of meta-heuristics that can solve this classification or function mapping type of problem. Another set of meta-heuristics are there that can be solved, that can solve optimization type of problem. So combining these two approaches or these two capabilities, we have combined them in a suitable way. to design multiband antennas. So the joint utilization of AN and PSO makes the procedure to bypass the repeated simulations. By using these techniques, the repeated simulation process can be bypassed. So when the only tool you have is a hammer, every problem you encounter tends to resemble a nail. So depending on the techniques available with you, the tools available with you, you choose those specific tools in a judicious way. Okay, and it should not be like this, like you have a technique available with you, and for every problem you go for applying that particular technique. That should not be the way, right? If it is a easy problem, if it is a simple problem, then do not go for these meta-heuristic techniques. If there is a requirement, the actual requirement, then only go for these meta-heuristics, otherwise not. Actual requirement means if it is a complex problem and having multiple number of minimas, maximas, then only go for this type of problem. So the conclusion is unconventional methods have been applied for solving unsolved problems in antenna engineering. Okay, if you study the literature, you will find lot of complicated antenna problems, lot of complex antenna problems have been solved using these meta-heuristic techniques. Not only ANN, but also the other techniques also, fuzzy logic, genetic algorithm, particle swarm optimization, ant colony optimization, BFO, many meta-heuristic techniques have been used for solving number of complex antenna problems. For further reading, you can see one of our book chapters that I have written in Modern Antenna Handbook by Balanis. Myself and Professor Kistus, we have written one book chapter on neural networks for antennas. You can see that particular chapter to find out what are the different ways of applying neural networks for antenna designing, where to apply, how to apply, when to apply. Those specific treatment bits you can find in this chapter. Application of neural networks in electromagnetics, a well-written book from Artec House. You can find a lot of applications of ANN for electromagnetic problems. You can find in this particular book, not only for antenna, for other problems also, how to use neural network that has been described in this book. Furthermore, another book, Genetic Algorithms in Electromagnetics, you can see this one. Although this book is specifically for genetic algorithm applications, but because the process of applying one meta-heuristic technique is not much different from applying to other. It's not much different from other meta-heuristic techniques or meta-heuristic based optimizers. So the way of applying these optimizers specifically for antenna designing or electromagnetics based problems, you can get that idea from this book by Hart and Warner. Thank you very much for your patience, Irene. And if there are any questions, I will be happy to answer that one.
Thank you, sir. Participants can clarify the queries with the resource person. If you have any queries, please put it in chat box also.
Hello, sir. Professor.
Sir.
I got a small fundamental question. How do you compare meta surface, meta material, meta heuristic?
So meta heuristics, see, meta material and meta surfaces, that is, you must be knowing the difference between those particular things. But meta heuristics is a method which basically deals with fixing the problem by trial error method. Fixing the design parameters or fixing the other parameters of particularly in electromagnetics we are talking in a trial error method. Okay. But in meta, when you are applying a meta heuristics, see, the trial error method that we are using is not completely random. It's a systematic way of applying a trial error method. Systematic way of applying. So, to reach a particular goal, you start with a random set of solutions, and using these meta heuristics, gradually you go for your best solution. So meta heuristics is completely different from those meta material and meta surfaces.
Okay, thank you, sir.
Okay, sir.
Hello.
Yeah, go ahead.
Sir, as you explained that the number of neurons in the hidden layer means we have to select based on the minimum error. So
right.
How to conclude that we are reached to the saturation, means there is no further improvement?
Okay. So when you are running that neural network training program, it's basically an iterative process, and with iterations, gradually you are fixing the weights.
Correct.
Right. Yeah. So there are situations where you will find even after applying a number of iterations, it is not affecting much as far as your final result is there.
Correct. Yeah.
Suppose in one case you are getting 5.003, another case you are getting 5.0031, right? Yeah. So suppose this type of case you are having after applying hundreds of iterations.
Correct.
So in that case, the number of neurons that you have taken is not sufficient.
Okay. Mm-hmm.
Okay. So there you need to gradually change your number of hidden layer neurons, because the actual computation is taking at that particular place, hidden neurons.
Yes.
So instead of increasing the number of neurons by a large margin, you gradually change with 1 or 2 neurons, 2-3 neurons. In that way, you go on increasing your hidden neurons.
Okay. Mm-hmm.
Okay. Then you will see appreciable result in your final answer.
Okay.
So basically, it's mostly is like if you have trained number of networks, you will get the idea. So the method, the approximate method of choosing the number of neurons is root over of ni dot n naught. Ni is the number of neurons in the input layer. N naught is the output layer neurons. But this is a approximate way. right? It is not sure that you are going to get your result if you are taking this many number of neurons.
Okay.
Okay.
Thank you, sir.
Yeah. So if there are no more questions, then I must thank you all for your patience hearing.
Thank you, sir, for your valuable session. I would like to mention the most observable points in this informative session, sir. The way you explain the concept with the practical examples are very useful. The detailed explanation of genetic algorithm makes us more clear, like training the artificial neural network for microstrip patch antenna, all are very informative, sir. I hope that the participants gained enough knowledge on meta-heuristic in antenna engineering. I wish to express my thanks to respected Dr. Amalendu Patnaik, sir, for spending his valuable time with us. Thank you, sir.
Thank you very much. So now I'm winding up the meeting.